layer perceptual neural network. So if you still remember, on last Thursday, we tried to deal with the handwritten digit recognition task. All right, we already loaded the data, explored data, and so we stopped at this step, build the model. Actually, we already designed the model. So we designed that, okay, for this model, after it accepts any 2D image, the first step we need to do is to get a flattened layer, because all the MLP neural network, they only accept some 1D input. So we first do the flattening, flatten it from 2D into 1D, right? After that, we will connect it with two hidden layers. Actually, the two hidden layers, both of them have 128 neurons and ReLU activation function. And then the output dense layer, we have 10 outputs, and we already know actually these 10 outputs represent the 10 probabilities. The probability for each class, for this handwritten digit recognition, we only have 10 classes from digit 0 to digit 9. So this is our design. So as you can see, building the neural network model is really like the building up some blocks. You just connect layer by layer until you get some outputs. And in last class, we also learned what is the ReLU activation function, the rectified linear unit function. Actually, we analyzed some of its advantages. Most of them concentrate on the efficiency. It's very efficient function. We also analyze one of its limitation. That's the dying ReLU problem. It may cause some dead neurons, which will never get activated because the left part, the gradient is just 0. And we know that if the gradient is 0, then that means it won't get updated. All right, so this is about the ReLU, but we still have one part missing. So the output layer's activation function. Here we said that the output layer is a dense layer with 10 soft max outputs. Then we need to look at what is this soft max. Softmax is another type of activation function. Actually, we already learned one activation function, which is called sigmoid. And we know that the sigmoid function represents probability, right? Because it has the output in the range 0 to 1, which is perfect matching with probability. But that's only one probability. If we can only get one probability, then we can only deal with binary classification task, right? The probability of some positive class. And then one minus this probability would be probability of some negative class. So what about the multi-class classification? Of course, sigmoid cannot deal with multi-class classification. We cannot use one probability to predict for multiple classes. Here we have another activation function called softmax. So the mathematical formula is that softmax for any class Zi. Here Zi is just some input number representing some value. Actually is the weighted sum for the class I. It should be the exponential of Zi divided by a normalization term. So this normalization term is the sum of J, where J is some node in the output layer, and we know output layer 1J is just one class, and the exponential of this Zj, we add everything up. So this is called the softmax. So you can regard such softmax as a combination of multiple sigmoids. Actually, it looks very similar with sigmoid, right? So basically, just 1 minus 1 plus exponential of some negative z. But somehow, we have these multiple sigmoids. We have to combine them up. We have to do some normalization. So that's why in the denominator is this sum term. It's a normalization term. We regard it as some combination of multiple sigmoids, and it calculates the relative probabilities. So it's similar to the sigmoid activation function. It returns the probability of each class. And now, actually, we can know why the denominator is like this, the sum. Because if the denominator is this way, then if we add everything up, then it equals to 1. That's the total probability, right? The total probability should equal to 1. So that is in the output layer. You can consider that previously, maybe we can just draw the output layer again. So we omit all the previous parts, is the MLP input and hidden layers. So we know that at the output layer, we have 10 nodes here. And the last layer is a dense layer. And for each output node, we know that it outputs some probability. This probability is exactly the softmax. This is the softmax. For example, output layer, we usually call it layer K. Then it's the K0, and this would be the softmax K1, and so on and so forth. The last one would be the softmax K9. In total, we have these 10 classes from 0 to 9. The softmax, it looks like in this way. Here, each Zi is just each of these Ks. Then we add them up, we can get that I from 0 to 9, this softmax Ki, if we add them up, that is equal to 1. This is the probability, right? And then each softmax outputs the relative probability. It's perfectly matching with the probability. Add everything up equal to 1. And each of them is in the range from 0 to 1. So this is the softmax. And for the softmax, it's mostly commonly used as an activation function for the output layer of the neural network in the case of multi-class classification. So basically, if you are dealing with a multi-class classification, and if you want to build a neural network to do this, use softmax at the output layer. It's perfectly matching with the multi-class task. Then some of you may ask that, why not use sigmoid for each of the nodes? Like, if in the output layer we have 10 nodes and each of them use sigmoid, is it okay? No, that sigmoid can only output one probability, and then that means you will output like the probability for this first class. You only consider the first class. You didn't consider the relative probability of all the classes. At that case, you need to do one more step of normalization or one more step of comparison to see like, okay, whose sigmoid is the largest, which is not convenient. Actually, you put some extra efforts to do this thing. That's why we directly use the softmax. So for multi-class, we won't use sigmoid. We only use the softmax. All right, so until now, any question regarding the softmax activation function and the overall design of our neural network, just like this way. Great. If no question, then later on, we will implement this one. We already designed all of the layers should look like this. Then how to implement that? Basically, you just consider, again, you are building up some blocks, but now using the HKUST library. Everything from the HKUST. You don't need to like implement anything by yourself. You only need to know the names of the layers, the activation functions, anything that you want to use directly. So build the model. First of all, we need to create a sequential object. So previously, I told you that the sequential in HKUST means neural network. If you consider the neural network starting from the input layer until output layer, it's just a sequential of layers. So that's why in HKUST it's directly called a sequential. If we create a sequential object like this, then we will create an empty sequential. That means we indicate that this model is a sequential model or a neural network model, but currently it's just empty. We just initialize it to be an empty. And next, we need to add the layers to this sequential model one by one. We know the first is input layer. Input layer is a flattened layer, right? So directly add this flatten. This flatten we already imported from HKUST. So this flatten, it takes these arguments, takes the input shape. We need to tell this input layer, okay, so what should be the shape? And for this input shape, we know actually is the x train dot shape, and starting from the dimension 1, because the dimension 0 is the number of training data. We're only starting from the dimension 1 until the end. So if you still remember what is X train, actually previously we already get here. X train's shape is 60,028. We don't need to consider the first one, it's just the number of training data, right? What we want to flatten is we want to flatten a 28 by 28 array into a 1D array. So that's why we start from X train dot shape 1 from this dimension 28, and then we give it to the flattened layer. So after we add this, now this flattened layer will know that, okay, you give me an input shape with 28 by 28. Then I need to do the flatten from the 28 by 28 into a 1D, that is 784. So after this, it knows that, okay, the input layer is 784. All right, this is done. As you can see, as long as you know what is the name of the layer you want to add and the argument, basically you just copy it. After that, we connect it with a hidden layer. So hidden layer, we know the first hidden layer is a dense layer, and we have 128 neurons. We use ReLU activation function, so we directly add this. So each time you want to add a new layer, call this function model.add, and then give the layer's name. So we give, okay, dense. So in this dense layer, we have these arguments, units. Units is the number of neurons you want to add. So in this layer, it's 128. Activation, you don't need to implement it by yourself. Even though ReLU is quite simple, but you don't need to implement by yourself. You just call it directly. Activation, you call this. It's a string value ReLU. Then it knows that, okay, you want me to give it a ReLU activation function. And we also have this thing. Previously, we didn't talk much about the regularizer. So theoretically speaking, it's okay that when you design that, you don't have the regularization term. But during practical implementation, usually we need this one. This regards to the loss in this layer. So this layer, we want to use the L2 loss. L2 loss, that means is the L2 times the reduced sum of the square x, and L2 is a regularization term. We add it to be 0.002, a very, very small number. Why should we just put such a small number here? The reason is actually we add a notation at the end. So we want to apply the regularizer to penalize the weights, which are very large, causing the network to overfit. So after applying this kernel regularizer, multiplying it by a very small number, 0.002, then the weights will become smaller. You can consider that each time when we update the parameters, actually we need to use the derivative of the loss, right? Then if we already multiply this loss with some very small number, then this small number will be multiplied into the change of parameters. So each time the parameter will only change with a very small scale, like multiplied by 0.002. That means each update step, your parameters won't change very largely. So it won't be very, very large. And this can reduce the overfitting problem. And some of you may also ask that we have another term to control the speed, learning rate, right? Why not directly set the learning rate to be such a small number? Why do we especially deal with the hidden layers? This is because actually we only want to penalize the hidden layers parameters. We don't want to affect the output layer, because usually the output layer is the first step when you update parameters. When you update parameters, you always start with the output layers parameters. Usually at the first step, it does not cause the overfitting very severely. So it's okay to just use the learning rate to control the output layer. But with the updating rules going on, that is with the backward propagation, after you update all the parameters here in output layer and you do the backward, it's easily to cause overfitting in some hidden layers parameters. That's why we specially penalize all the hidden layers parameters change, and we add the regularizer only for hidden layers. So that means all the hidden layers parameters, when we calculate their change in this practical implementation, it's not only multiplying the learning rate, also multiplying this term, this L2 term. So make it very, very small. Each time the change is very small. And this is our first hidden layer. Then basically the second hidden layer, you copy everything because second hidden layer is the same with the first hidden layer. So add another layer, dense layer. Basically it's everything the same, but as you can see the activation will change to be activation dot ReLU. So if you still remember how we import these activations, you will find that, yeah, we need to back to here. Actually, the activation is imported from the TensorFlow.keras. So if we use activations.ReLU, then that means we are using the ReLU activation function implemented in TensorFlow.keras. But if we directly use ReLU string value, so here, this one, then that means this ReLU is already implemented in this dense layer. It's arguments in this dense layer, and the activation can be string value ReLU. So actually we are calling different libraries, even though they are both ReLU activation function, but they are from different libraries. Both are okay. So these two lines just to show you actually you have very large flexibility, very large freedom to choose activation functions. Basically, you can directly import from keras or import it from the TensorFlow.keras activations. Both are okay. After two hidden layers, we get our output layer. We add another dense layer. Dense layer now, the units is only 10. We only need 10 outputs. The 10 probabilities and activations, we let it to be soft max. And we are done. Basically, after you add all the layers you want, you finish building the model using keras. Just like building up the blocks one by one, starting from an empty sequential model, add all of these one by one. All right, so any question regarding how to implement using the keras? As you can see now, totally different with what you have done for the previous labs, right? Previous labs, you have to implement everything by yourself from scratch. But now, what you need to do is you need to read the documentation from the keras, and then you know, okay, which layer you should add, which arguments you should specify, then everything is done. All right, so after we build the layer, usually we need to check our model. Right? We don't know whether our implementation is correct or not. Sometimes we don't even know whether our implementation is consistent with our design. If you want to check that, we don't recommend you to read your codes to check that because it's not so readable, even though it's still very clear, but not as readable as you directly print your model summary. So this is provided by the keras. If you directly print this one model.summary, you can just see everything very intuitively, very straightforward. So you don't need to look at your codes to know which are your layers. You directly see from here. So if we print this model summary, we will say, okay, our model is a sequential model. Definitely, we initialize it to be a sequential. And then all of our layers are here. The first layer is a flattened layer. The output shape is known, 784. What is this known? This known is by default, it will put there. Basically, this known is that it occupies the first dimension, dimension 0, to represent the number of training data later on. Because later on, when you train your model in some real training data, the first dimension always specifies like the number of training data you give to the model. But until now, actually, we are still at the step build the model. we haven't started to train our model. So that means our model does not know how many training data there will be. And also the number of training data will change, possibly may change. In this case, it does not know the exact number, but it must leave this dimension, keep this dimension for the number of training data. So it just put a known here, representing, okay, later on we will accept some training data, but currently we don't know the size. As you can see, the output shape, the first dimension is always known. Leave the position for the number of training data. And then so basically you only need to look at from dimension 1 after known what are the numbers. So after flattened layer is 784, right? Just 28 by 28. You do this multiplication. A number of parameters 0, because during the flattened layer you don't do any computation. You directly convert a 2D from 1D. There is no parameter associated with this layer. It's simply an input layer. After that, we go into our first hidden layer, dense. After the dense layer, we have output shape known 128. 128 comes from the number of neurons, because we specify, okay, for this layer, number of neurons is 128. So of course, after this layer, the shape becomes 128. And the number of parameters is here, this 100,480. Later on, we will talk about how to calculate the number of parameters. So for now, we just look at all the layers. Next, we go into the second dense layer, our hidden layer 2. It just gives an index dense 1 because the dense is already occupied here. And after this hidden layer, again, output shape does not change. It's still 122 because the number of neurons is still 128. And then it can calculate some parameter numbers. Last, we will have our output layer, again, dense layer. And after the output layer, the shape becomes known 10 because we have 10 output nodes here in our output layer. So it's 10. And also, it can get the number of parameters. So after all of the layers, it will show this layer one by one, very clear. And then it gets you the total parameters, the trainable parameters, and the non-trainable parameters. So for this case, of course, all of the parameters are trainable parameters. That means all of these parameters will get updated during the training process. But still, you may ask this. Now, how to calculate the number of parameters in a dense layer, right? How do we get all these numbers? Here we provide this formula. This is a general formula for dense layer in neural network. Consider that the number of parameters. In a neural network, we know the parameters, there are only two types of parameters. Weight parameters, bias parameters, right? So basically, the number of parameters means the number of weights plus the number of biases. We just need to consider, okay, what are the numbers for these two? Number of weights. In a neural network, we know each edge is associated with one weight. If we want to get the number of weights, then that means we want to get the number of edges we have. And in dense layer, we know that actually each node in previous layer is connected with each node in the current dense layer. So that means the number of edges between these two layers actually is like this. The number of previous layers nodes times the number of current layers nodes, because fully connected. These are the number of edges we have. And now we get the number of weights. Then what is the number of biases? Number of biases, we know each neural node itself has a bias term. So dense layer here, each node, it has a bias. So that means now the number of biases is just the number of current layers nodes. And of course, you can rewrite it to something like this. So the number of parameters in any dense layer in your neural network is just the number of previous nodes plus 1 times the number of current layers nodes. And after you have this formula, you can easily get the number of parameters in each layer. Like for this dense layer, if we follow that formula, then it should be 784 plus 1. That's 785 times 128. And then we get this number. And then for each of the layer, actually they are all dense layers, we can easily get a number of parameters. All of them are trainable parameters. Of course, we need to update all of these parameters. And you may ask that at any case where we have these non-trainable parameters, actually that's arguments you can control. So previously when you built the layers, actually I think there is, I can't exactly remember the name, but there is a parameter, it's like trainable or not. That means if you set that trainable parameter to be false, and that means you are indicating in this layer the parameters are not trainable. So they will keep fixed. They won't change. But usually we won't do that. We won't freeze any layer. We just want to update all of the layers. So usually the non-trainable parameter is just 0. Everything is trainable. So this is by printing the model summary. You can also try to plot the model. Basically, you just get a very similar thing like this. So plot model, it gets like first the input layer. In this one, it does not return a number of parameters. It returns the input shape and output shape for each layer. The first dimension is always left as the known or question mark, means that it's the number of training data later on it will receive. So the first dimension just keeps it empty. It's okay, let known be there. First input layer, input shape is like this known 28 by 28, and output layer is known 28 by 28. This layer is that before you go into the flattened layer. Basically, that is what the input it receives. And then this is the flattened layer. After receive 28 by 28, it outputs like 784 flattened layer, and all of the dense layer, the hidden layer 1, hidden layer 2, and also the output layer will just keep the same thing with here. Basically, they are the same thing, but this one is more like plotting the model, but this one is more like listing all of the layers. You can just choose these two ways to try to get your summary so that whenever you want to check whether your model is correctly implemented, consistent with your own design, you can like refer to this table, compare it with your own design to see anything wrong. All right, so any questions so far regarding the model summary? Great. Then we finish the step build the model. Next would be compile the model. Before you train it, you have to compile it. So compile means that you need to add more configurations so that it knows how it should be trained. So in this case, we must specify 3 very important things. The first is optimizer. If you still remember the terminology we have learned, optimizer is the optimization algorithm we will apply here. And we also need to specify the loss. The loss is the loss function of the whole neural network. The whole neural network basically means that the loss function we use at the output layer. Because at the output layer, the loss function is a true loss function for the neural network. And we also need to specify some metrics. This metrics, of course, it's not exactly used for training, because we know for training, we only need loss and optimizer, right? We define a loss, then the neural network, its only objective is to minimize the loss. How it minimizes the loss depends on the optimization algorithm. If we just want the model to train itself, we only need these 2 things. This matrix is more for us. Like each epoch or every a few epochs, we can try to monitor how our model performs. In this case, we can define like some metrics here so that later on we can always try to monitor, okay, what is the evaluation metric in the validation sets. So let's see them one by one. So now we only know we need to specify these 3 things, but what are them? So here we create an Adam optimizer like this. So that means we will select Adam as our optimization algorithm. So Adam is like a much more advanced version of the gradient descent. So it's also based on the gradient descent, but improved a lot. So basically, I think it's one of the state-of-the-art optimization algorithm we will use to train the neural network. Usually, we directly use this atom. It's most of the cases it performs the best. And we set the learning rate to be 0.001. Usually, the learning rate is a very small number. And okay, this is the optimization. And next, we configure the loss function. So here, as you can see, we use the sparse categorical cross entropy loss. This is the cross entropy loss function. Usually, this loss function will be used to do the multi-class classification. Later on, we will also talk about this loss function, but let's just finish the matrix. Matrix is just the metrics you want to monitor during the training. So here we let it to be accuracy. And that means every a few epochs, it will report the accuracy for you. Like during the training, like for example, after the first epoch, it will tell you that, okay, what is the accuracy on the validation set after it trains for one epoch. And so that you can always see how the performance of the model like goes on. This is first, of course, you want to see like whether your model converge or not. So you can through this metric to see that. Another thing that you want to avoid overfitting. So that's why we need to monitor the metrics. Here we just set accuracy here. Of course, you can add more metrics. As you can see, this matrix argument is a list. You can just put as many metrics as you want inside this list so that each time it will like calculates all of these metrics for you. You can add like F1 score, precision, recall, something like that. All right, so configuration, we are done, but you don't know what is categorical cross entropy loss. If you have taken some statistic course, possibly you'll know that, but it doesn't matter if you haven't learned it. The cross entropy loss is also called a multi-class cross entropy loss. So as you can see, specifically designed for the multi-class. Mathematical formula is that, so this CCE, this loss, is the negative of the sum of yi times log pi. So here y, this y represent the actual labels. Usually it's the one-hot vector. And p represents predictions, usually the output of the soft max. By the way, what is the one-hot vector? One-hot vector means that now it's a vector with many zeros and only one. That means only the class, the true class label index has the number 1. So maybe we can try to use an example to illustrate that. Okay, so suppose now we have a data. This CCE is for single data. This formula is defined for some single data. So suppose for any x, and its true label is 5. That means y is 5, but actually we cannot directly use 5 as a y. As you can see, y here is a vector. It has the index yi, right? We first need to do one-hot encoder. One-hot encoding is that now we know we have 10 classes. 10 classes, so we will convert it into a vector with a length 10. And then the first one is 0, second one 0, third one 0, first one 0. 0, 1, 2, 3, 4. Only here it has 1 because its class, the true label is 5. So that means only at the index 5 it has 1 here, and all other index is 0. And this vector, it has a length 10 because in total we have 10 classes. And so now each of the row here represents one class. This represents the class 0, class 1, class 2. It has label 5, so class 5, it has the number 1 here. This is the one hot encoder. So this is the index. Okay, that means for any tune label, we first need to do one hot encoding so that it becomes a vector y here. And then we can compare this y with the output of all these PIs. What are these PIs? Basically these things, all of these softmax. Previously, we can, from the output layer, get 10 probabilities, right, from the 10 softmax. And then we just compare this y with this p using this formula. This cross entropy loss. And actually, this cross entropy loss is a very general concept in the statistics. So it's most used to measure the distance between two distributions. If we have two distributions, we can define what is the distance between two distributions, and it's usually defined using this cross entropy loss. You can consider that here y is a distribution, right? And of course, this softmax distribution, they are all the probabilities. And this you can also regard it as a probability because only class 5 has a probability 1. All of others have the probability 0. So basically, just measure the distance between these two distributions. So specifically for multi-class classification task, we can consider it tries to measure how close the predictions. Predictions is the model distribution. Predictions is all of these PIs. And with the actual labels actually are data distribution, the true distribution in our data. So it measures how close the predictions are to the actual labels. We usually use this categorical or multi-class cross-entropy loss to define as the output layers loss. And here we use this one. But of course, we use some sparse washing for the efficiency. This is for some practical implementation case. All right, so until now, any question regarding the model compilation? Great. If no question, then let's take a 5 minutes break. After the 5 minutes break, we will continue to go to the next step, that's train the model. Later on, when you add some layers, then it becomes all of them actually the model itself is still a sequential object.
不是，我记得全国高考那天我一直算那个期望不还有什么？
Yeah, we haven't started the training, so actually does not know how they can see. Yeah, no, actually, never specify because this one it means that we just leave a position.
那我们高二的时候上面专业的时候做过你这个。因为我也做过好多乱七八糟的，大部分的不行。
After building the model, actually, you can also create some other ones. So that's why this is a general model for training.
那个我们还是9组不赢呀，9组不赢。他第一位是让你算多少？就比如说2分之1看你算多少，我赢了1块，输了1块，带了5块，对啊，弄几次就行。我说这个我们曲折无穷的希望，这个就是让你解释一下这个是什么意思，最后一小段让你们主管解释这个是什么意思。没错，看谁可以讲，这个是什么？ 这是什么？而 2711的作业。
You can type cluster.
Oh,
really? Yes. But the thing is that it's hard.
刚刚你做那个题，它有什么特别之处吗？
You know, after using this for so long, if they ask me
你为什么专门让我做这个？ 哦，你是要连续的。这个题它不是了。这个直球那个。刚刚那个题，还有题就是3投一定的正面概率为 P， 然后呢，任意场出现2次为题，没有连续的，就任意看2次题，那么最多就抛3次嘛。对，都抛3次，然后就没了呀。最多抛3次，然后就把所有的一个举一遍。
I'll get to that and try to understand. Like I'm on 1B.
给到那个对，直升最后对，然后 learning rate 大家都成，对 learning rate 都成。
Yeah, because I wasn't bothered to write everything.
说他现在那个 learning rate 不是一个很大的数，那不是意味
I
着
keep
那
writing
个
things wrong, so I need to like
显不
move
显
everything down a little bit this one.
对了 ，opposite。
And
它是不是back propagation 这个是
那它一层一层的，对一层一层，那你这个其实怎么说呢？一道浪打过去，再一道浪打过去，你每一道浪打过去，最后一个的变化其实比前面非常非常小，那一个是前面剧烈，前面几乎变不出来，那右程的右程的。
是一次update 一层的那个应该他们 update 的次数应该一样不一样，对，
就只是总一步的，就是每一次 update 的前面的那个这个移动幅度会很小。
我差不多为了避免过那个波
哦，你这个那为什么最后一个就不要长？每个人，因为就是跟过你和最后那个。
我就是这个 yesterday and I remember because it was 1:30.
每一次这个移动，那为什么说对于就是为什么我们就要排除这个最后一个那个这样做一个？
因为
是从 backward propagation 它们
don't like it. You know, you I don't know. Shut up. I couldn't answer half the paper. It was so hard.
哦，那意思就是因为这个没有说前面。
After 1 hour, I just leave. Like, there's no point. I thought it's gonna hate her. I don't know.
现实的放大情况。
People like a dictionary. I saw the paper and I texted there's a whole ass dictionary on my chair. And you know where I was sitting? I was in the very first row, the very center. My view was shit. And then this TA, can I understand the question?
这就只是笼统的错误。
I just trying to understand the question. I don't understand it after reading it.
但是这样成这个东西，就这个 output layer 前面这个倒数第一个这个 hidden layer 不相当于没用了吗？
很小。
那就相当于没用。
还是有用，就是你训练的 echo 不够多还是有用。对，因为基本上这种neural network它其实实际训练起来可能就会
You know, I saw this copy
这样
where
它训练 echo 不够多，它其实就相当于它就是让它慢慢。
which has a copy where and the copy where is shit. And shit. Non-stop.
现在就是这个。
对。
Alright, so let's come back. So now we already built the model, compiled the model, and we are finally get ready to train our model. Usually to train our model, we want to store all of the training history. Like it's not only like training in some code cells and then you just leave it there. Usually you want to store all of the log files. Log files mean the training history. So we create a TensorBot. TensorBot, which is a visualization tool, enable us to track the metrics like loss and accuracy, and also visualize the model graph, view the histogram, so that you can store all of the training histories in your some like local files or in your Google Drive, so that later on you can just look back to see like maybe something goes wrong, or maybe at some steps you already converge, or at some steps you started to overfitting. You want to track that. So first create the logdir. Because possibly you will train your model for multiple times, you don't want to like overwrite your previous training history, so you can add a timestamp by using this datetime. So usually it's just call the current time, datetime.now. After that, you can convert it into this format, so like which year, which month, which day, at which hour, which minute, which second. Actually, it can like as accurate as some second, and then add it as a timestamp to the name of log's phase, so that later on you can directly read from your file name to say, okay, which day it comes from. And after that, create this TensorBot. Run this TensorBot logdir. Logdir is that where you want to store your log file, and this histogram frequency. Histogram frequency is that after how many epochs you want to view your metrics. Here we set it to be 1. That means each time, each epoch, after it trains itself for each epoch, it just reports all of the things you want, including the loss function and also the metrics you want. Of course, you can also set it to be some larger number if you don't want your TensorBot to be so noisy, because if like every epoch it just print out something, it's sometimes quite noisy. For example, you can set it to be 5 to be 10, so that you monitor your training every 5 epochs. And next, train the model. In Keras, the training is also called the fit, which is same with the scikit-learn. If we see this method fit, then that already means the training. So in this training, we need to give the training data and the training labels X train, Y train. And we also need to tell our model how many epochs we want. We let epochs to be, this is the global variable we have defined before. Epochs is 1, we just train it for 1 epoch. And we can also give this argument of validation data. Validation data is that's after the 1 epoch, because we set the histogram frequency to be 1. After this number of histogram frequency epochs, it will evaluate the current model on the validation data set to see how it performs. This is basically, you can use it to decide convergence and also to decide whether you are overfitting or not. And then for this callbacks, it should be the TensorBot callback we created just now. We want to store all of our training history in this object. And after you run this line of code, this training history, be model.fit, it starts to train, and it will stop after it trains for this number of epochs on the training data. So for train the model, basically it's just such simple. You create some TensorBot and then run the train function. And after that, we finish training, and we can try to evaluate our model accuracy. Evaluate model, of course, we need to call some function. In Keras, it's directly called the evaluate. So you run this method, model.evaluate, give the testing data and testing label to this model. And note that actually we kind of treated the model, because previously the validation data is also the testing data. So actually the testing data is already seen by this model before we start to do evaluation. So here we let it evaluate on testing data and get the validation loss and validation accuracy. After that, we can print that. We find that, okay, after training, for one epoch, the validation loss is 0.2004 and the validation accuracy is 0.9646. Very high, right? Even though we only trained for one epoch, the accuracy is already very high. That means our model, our design model, is very appropriate for this task, and our training data is already enough to let the model learn from the data and to get a very good, very precise model. So next, we save the model because we find that, okay, our model performs quite good. We can use it later. So we save the entire model into a HDFS file. That's the Hadoop distributed file system. We use this .h file extension to indicate that it should be saved in this format, HDFS file. Actually, I think in your lab or in your PA, actually you are required to save it as some HKUST extension, which is also a file format in the HKUST. So actually you can just choose both ways, but in PA and in lab still you need to follow the instructions. So here we show you an example of this HDFS file. So directly let the model be digits recognition MLP.h file and then save your model by assigning the model name and save format to be H5. After you save the model, it's already saved either in your local file or in your Google Drive. If you are running in Google Cloud, then possibly it's in your Google Cloud. And after that, you can reload your model to use that. This is how we do that. The loaded model just be load model and give the model name. Load model is a function we already imported during the step 1. Import this function and then you can directly use that. Now you retrieved your model which you previously saved into this one loaded model. Alright, after you get your model, of course you need to use that. So use that later. So to use that, we can use this predict function. Predict means that, okay, now we go into the prediction step, right? Previously, all of the previous, actually, basically, there's some training. Then after training, of course, you can do prediction. We use this model to do prediction by specifying which images you want to predict. We call this method predict. So loaded model.predict, give this X test as the input and get all of these predictions. If you print this prediction shape, you will find that the shape is 10,010. 10,000, of course, is the number of testing data. We know X test. In this X test, we have 10,000 testing data. And this 10 is the 10 softmax, these 10 probabilities. Because after the model, after our MLP model, at the output layer, it must output 10 numbers. We have 10 nodes there, right? So for each of the testing imagery, we will have these 10 probabilities. The predictions has such shape. You can also print out all of these predictions by using the pandas. Because in pandas, you can see like relatively convenient to see all of these numbers. So each prediction has 10 numbers. Each row is one testing data. Each column is for the class. We have class 0 to class 9, which means the 10 probabilities. And if you look into it, for example, the first data point, it has the 10 probabilities like this. Most of the probabilities are very, very small. Only one is quite large compared with this one. So for this class 7, it has a probability 0.9996. But for all other classes, the probability is relatively small. So that means actually our model, during the prediction, our model has the highest confidence to to assign this data into the class 7. Now, of course, the prediction result should be the 7. For each of the data sample, actually, you can get the probabilities, 10 probabilities. And later on, what we want to do is that we should classify the imagery into the class with highest probability, right? Then, starting from such a 10,000 by 10 array, how to do that? How to get the final classification result? Just by using some NumPy function. This is, yes, excellent, max. This is what you have learned before in advanced Python programming. Directly use max or argmax. Max is that you're selecting the maximum probability. Argmax is you retrieve the index of the maximum. Here we want the final classification result. We get the argmax. So extract the predictions with highest probabilities. And note that here the axis should be 1. Axis 1 is that along the column direction, because we want to select the highest probability in the column direction. So let axis be 1, and then we can get that. So if you print out these prediction results using pandas.dataframe, you will get this one. Now it's a 1D array actually. 1D array with the shape 10,000 consists of the final classification results for each of the testing data. As you can see, previously we already analyzed that the first data should be classified into 7. So it just wrote here. All right, this is how you can use your model to do predictions for some new data. And you can also try to display more. For example, we can here display the first 196 images. And then we, here basically these things are just specifies all of the arguments you need to visualize your results. After that, we can get something like this. This is the first 196 images, and most of them are correctly classified. We use green, this color, if the classification is result, and if the classification result is wrong, we use the red color. So among these first 196 images, only 2 are wrongly classified, like this one. The classification is 6, so our model thinks this digit is 6, but actually it's 5. But as we can see, this is because the handwritten digit itself is very confusing, right? So our model is not very well capturing such confusing or misleading handwritten digit. Another mistake occurs here, which is also quite confusing. Our model predicts it to be 4, class 4, but actually it's 2. Which is another wrong prediction. But until now, our model is only trained with 1 epoch. If we train for more epochs, it's possible that we can try to avoid such mistakes. All right, so after using our model to predict for the new data, we go into the last step. We can try to plot the confusion matrix for our prediction results. We know that confusion matrix shows what numbers are for each prediction case, right? We have a 2x2, not 2x2, we have a 2D matrix, and the row, usually the row represents the true labels, the column represents the predictions. You can just count all of the numbers here, like what you have done in the midterm exam. But in the implementation, you don't need to count by yourself. We can directly call the confusion matrix, which we imported it before. So by running this function, it directly computes the confusion matrix from the true label white test and the prediction, that is the prediction results, and then show in this figure. So we can try to analyze more on the performance of our model. We know in such confusion matrix, all this main diagonal represent the true positive, right? That means the true label is consistent with the prediction. That's the true positive. And if we look at this one, we find that the true positive is quite large compared with all other entries. Means that actually our model performs like quite good on this data. And we can also try to see from the other entries to get a sense about like in which case our model tends to make mistake, we can try to find some large numbers. For example, here is a large number, relatively large, 26. 26, and we find that 26 is the true label is class 7. So here, class 7, the prediction is class 9, and this number is quite large, means that our model tends to make such mistake, tends to misclassify with some 7 into 9, which is understandable, right? Because we know 7 and 9, they are just similar, these two digits. And some other large numbers, actually we can also, I think this relatively only this one is quite large. Some other large like the 17, like the digit 8, sometimes also tend to be classified to be the class 9. We can also find some zero entries. Zero entry means that our model never made such mistake. Like here, this is a 0, true label is 6. And then the prediction is 9. That means our model never misclassifies some 6 into 9. Of course, because these two digits like are quite dissimilar with each other. So we can like refer to this confusion matrix to analyze more about our model performance. And this is the protein confusion matrix. And basically, until this step, we finish it. Previously, we said that in our whole procedure, we have these 10 steps, and we finish all of them. So until now, any question regarding this handwritten digit recognition task? Great. Yeah, as you can see, we go into a totally different style. Just import everything you need and try to get the existing modules, which is quite different from what you have done in the first half semester. Next, we will do some analysis on the multi-layer perceptual neural network. Let's first see a problem of the training, MLP training. That's called vanishing gradient and exploding gradients. This is one of the common problems of training a neural network, especially with many hidden layers. The more hidden layers you have, the easier you will encounter such problem, vanishing and exploding gradients. So when we train a neural network, the gradient, or we know that the gradient basically in 2D is just the negative slope. The gradient can get very big or very small or exponentially small, which makes the training very difficult. We don't want the gradient to be too large. We don't want it to be too small. Both cases are like preferred to be avoided. We want it to be in some proper range. So as a consequence, if the gradient is very big or very small, then the weights are not updated anymore. So basically, the learning just stalls. So this is the vanishing gradient. Vanishing gradient means that now the slope or the gradient just decreases gradually to a very small value and makes the training difficult. Because we know if the gradient is close to 0, then that means there is no change on the parameters. In that case, the learning stops. Even though we haven't converged yet, we haven't go to some local minima, but just because the gradient is too small, we cannot perform the learning. And the exploding gradients is that the slope or the gradient grows exponentially to very, very large. If it goes in this way, then eventually it will just exceed the precision of Python. Then everything just becomes not a number, NaN. That's why the learning also stalls if the gradient is exploding to very, very large. And we want to avoid these two cases. Then how to know whether your model is suffering from vanishing or exploding gradients? So for vanishing gradient, if you find that the parameters of the higher layers vary dramatically, but the parameters of the lower levels do not change significantly for vanishing or not at all, then possibly you are suffering from the vanishing gradient. Higher layer means that like the output layer and the layers close to output layer, and lower layers means the layers close to the input layer. So that means you only like update your parameters in some higher layers, but all of the previous layers, they do not change, almost do not change. And that's possibly because of vanishing gradient. And during training, if you find that the model weight just becomes 0, that's also possibly because of the vanishing gradients. And if you find the model learns very, very slowly, and after a few cycles, the training just becomes stagnant, it's also the vanishing gradients. So these are some signs that you're suffering from vanishing gradients. And then for the exploding gradients, if you find that your model parameters are growing exponentially, that's definitely exploding gradients. And during the training, the model weight just becomes not a number. That's exploding gradient. Because after it increases exponentially, it just exceeds the precision of Python. The Python cannot support such a large number, so everything becomes not a number. And then the model goes through an avalanche learning process. These are some signs that you are suffering from the exploding gradient. Later on, we will also talk about how to avoid or how to try to like alleviate such vanishing or exploding gradient problems. Basically, that depends on how you can select a good activation function. But for the exploding gradient, actually we have another thing to control that. This is previously I mentioned that by setting some regularization term in hidden layers. Previously, when training our model, actually in our hidden layers, we set the regularization L2, let it to be a very small number. This is in order to prevent such exploding gradients in the hidden layers. Another problem, quite common, overfitting. So overfitting refers to a model that models the training data too well, very well. It happens when a model learns the details and even noise in the training data to the extent that it negatively impacts the performance of the model on the new data. It's too good on training, but cannot do anything on the testing on the new data. And underfitting refers to a model that can neither model the training data nor generalize to new data. Basically, this is a bad model, a failure model. It cannot do anything. So if we look at some examples, we can see it's like this. For regression, if our data looks like this, then our optimal fitting actually is this one, right? We know that it's ideally this one, but underfitting that we want to use, somehow we want to use a linear decision boundary or a linear model to estimate such non-linear model. Then this underfitting. Overfitting means that now basically we just try to model all the noise here to get a very strange model like this. Of course, in this case, possibly you will have very high training accuracy, close to 100%, but when it's applied to some new data, it just failed. And for our classification problem, like if we have a non-linearly separable data like this, our ideal decision boundary is like this. And of course, if you use a straight line to separate them, it's underfitting. It does not train very well on the training data. But if you want to consider all the training data points, including the outliers, including the noise, you will get a very strange decision boundary like this to try to get the 100% training accuracy, which is also not good. What we want is some optimal fitting like this, right? You can also consider that this problem happens like when you are doing the past exam paper, that's training, and when you take the exam, that's testing. If you train too well on the past exam paper, possibly you only know how to do the questions on the past exam paper. You train very well. That means if I give you a past exam paper, you can get 100 points. But then you cannot generalize too well on some new questions on the exams. That's the overfitting. Underfitting is that possibly you didn't review the past exam paper too well. Then you don't know how to do past exam paper, don't know how to do the exam questions. And what we want is some optimal fitting here. Like after learning, after training on the past exam paper, you can generalize very well to some new questions, even though you haven't seen these new questions. So these are the problems of overfitting and underfitting. In neural network, usually it's the overfitting happens. In neural network, it's easy to avoid underfitting. In order to avoid underfitting, you just add more layers, add more nodes. You can definitely avoid underfitting. But how to avoid overfitting is more challenging. This happens more in the neural network training. And next, we still have a few minutes to cover like how to design our model. Previously in the handwritten digit recognition, I directly show you the design, right? Tell you that, okay, now we have these two hidden layers. Each hidden layer, we have 128 neurons. But how did we come up with the design? Like how many layers and number of neurons in each of these layers should we select? Especially in lab 6 and in the future, you have lab 8 and you also need to deal with PA2. You need to decide this. You need to decide that how many layers you want to choose, how many neurons you want to use in each layer. The input layer is quite simple. Number of layers is just 1. We only have 1 input layer. And the number of neurons is just the number of features, that is the columns in our data. Like for the exclusive OR, the number of neurons in the input layer is 2 because the dimension of the data is just 2. Input layer is quite simple. Output layer is also quite straightforward. Output layer, we only have 1 output layer. A number of neurons, mostly 1, unless the softmax is used. Like if you are dealing with multi-class classification tasks, then you have multiple neurons, depending on how many classes you want to predict. Other cases, the number of neurons in output layer is just 1. For input and output, they are quite straightforward. The trouble happens in the hidden layers. It's not trivial to decide for the hidden layers. The hidden layers, first let's look at the number of layers. If our data is linearly separable, we are so lucky. No hidden layer at all. You can use a single neuron to learn that, to learn any linearly separable data, right? If data is not linearly separable, but somehow it's less complex and only has a few dimensions or features, then the neural networks, usually you can set 1 to 2 hidden layers. It can already work very well. If you find that your data is very complex, has large dimensions or features, usually you can choose to use 3 to 5 hidden layers to get some optimum solution. And then let's look at the number of neurons. Number of neurons, it should be between the size of the input layer and the output layer. So like previously, we have 784 nodes in the input layer and we have 10 nodes in the output layer. So the hidden layer's number of neurons should be between these two numbers. And here is sum of rule. The most appropriate number of hidden neurons, usually you can refer to this one, the square root of input layer nodes times output layer nodes, just a sum of rule. And by convention, we also follow this rule. So the number of hidden neurons should keep decreasing in subsequent layers to get closer to pattern and feature extraction, and then identify the target class. Keep decreasing. So it's not happen frequently. You get some more nodes in the next hidden layer than the previous one. So you should just keep decreasing. All right. This are some general use case, only general use case. They can be modeled according to the use case. That means they are not absolute correct. Still, it depends on your own specific task, your own specific data you want to deal with. This is not always correct. You can refer to them. These are some conventional rules, but not the absolute rules. So sometimes the number of nodes in the hidden layer can also increase in the subsequent layers, and the number of hidden layers can also be more than the ideal case. This depends on the use case and problem statement that we are dealing with. Usually, you still need to adjust your model structure by yourself to have different attempts and to see which is best for your data and for your task. And usually this requires some time to choose. Actually, this is the difficult part in the neural network training. Like even though now you don't need to implement everything by yourself, you can just directly import libraries, but how to select a good structure is challenging. Really, especially for some complicated data. Actually, when the researchers, the AI and machine learning researchers, they want to train a data, they want to finish a task, usually they need to spend lots of time to select the best structure to train their data. All right, so until now, any questions so far regarding the neural network design?
Do we need a convolutional neural network before reflection?
For MLP, we don't need that. Later on, when we are learning convolutional neural network, CNN, we need convolution layer. For MLP, just everything is just follows the 1D. Yes.
So kernels regulate is just for calculating the loss, and then you use the Adam thing to, and then you utilize the Adam function to compute the loss with the gradient.
Yes. Yes, Adam used to optimize the loss function. Yes. Yes, very good. Thank you. Any other questions regarding the design of MLP? All right. So currently, we only have like some general rules of like the number of layers and number of neurons. We still have a very crucial part. That is how to select activation function. So that will be left to the next class. So next class, we will continue with the analysis on MLP and see you on next Tuesday. Next Monday and next Tuesday, please remember to attend the lab 6. The lab 6 will again require your attendance. So see you in next week.